बिस्मिल्लाहिर्रहमानिर्रहीम अस्सलाम वालेकुम। कैसे हैं आप? दिस इज लेक्चर नंबर 24. लेट्स स्टार्ट. So first we take a review of last lecture. In last lecture we discussed Poisson probability distribution with related examples. Then we discussed hypergeometric distribution and multinomial distribution and the negative binomial distribution. So the objectives of the current lecture. In this lecture we are going to discuss probability distributions of a continuous random variables. What are the probability distributions which we can use when our variables under consideration is a continuous random variable, and in particular we will keep our focus on the uniform distribution, and we will also discuss properties of uniform distribution and several examples which are related to the same distribution. So let's start. So continuous probability distributions. Some of the very important continuous probability distributions which are most commonly used, they are the uniform distribution, which is also called rectangular distribution, which is the focus of today's lecture, and then normal distribution, the t distribution, and the exponential distribution, the chi-square distribution, the beta distribution, and the gamma distribution. So as far as this lecture is concerned, we will keep our focus on the uniform or the rectangular distribution, and even in our next lecture we will discuss the normal distribution, which is mostly used and most comprehensive distributions, and we will also see certain important features of the normal distributions in our next lecture. So as far as the exponential, chi-square, beta, gamma and t distributions are concerned, we will not consider these distributions in this course, and you will study these distributions in some advanced course. So let's start. So uniform distribution. A uniform distribution is a type of continuous random variable such that each possible value of random variable x has exactly the same probability of occurring. So uniform distributions, as the name suggests, that uniform mean having same probability. So having uniform probability or same probability of occurring. So if a random variable follows the uniform distribution, so it means that random variable will have the same probability of occurring for each possible values of the same variable. So uniform distribution. A uniform distribution is a type of continuous random variable such that each possible value of random variable x has exactly the same probability of occurring. The uniform distribution, as the name suggests that it has the same probability of occurring. So uniform probability of occurring or the same or equal probability of occurring. So as a result, the graph of the distribution function or the probability distribution function of random variable x, which follows a uniform distribution, it is a horizontal line and it forms a rectangle with the x-axis. So hence its secondary name is the rectangular distribution. So in common with all continuous random variables, the area under the function between all possible values of x is equal to 1. Since we know that in each of the probability distributions the total area is 1, so here in case of uniform distributions it also has the total area equal to 1. And as a result, it is possible to work out the probability density function of x for all uniform distributions using a simple formula. So we can use one simple formula to get the probability density function. Uniform distribution. So a uniform distribution is a type of continuous random variable such that each possible value of random variable x has exactly the same probability of occurring. So uniform distribution, as the name suggests, that all possible values of random variable x have the uniform probability of occurring. So uniform mean the same probability of occurring or the equal probability of occurring. So since the probability is of all possible values of random variable x, the probability is same, so as a result the graph of the function is a horizontal line and it forms a rectangle with the x-axis. So here is the random variable x, and on y-axis we have the corresponding probabilities. So this random variable, suppose it ranges from 0 and 1. So all possible values of this random variable from 0 to 0.2, then 0.2 to 0.4, then 0.4 to 0.6, then 0.6 to 0.8, and then 0.8 to 1.0, and then 1.2, and suppose this is 1.4. So we have uniform distribution from 0 to 1.4. So you can see that the height of all the bars from 0 to 0.2, so from this interval from 0 to 0.2, this height it has certain value which is actually calculated by 1 over the upper limit minus the lower limit. So 1.4 minus 0, which is 1 over 1.4. And similarly the height of this interval from 0.2 to 0.4, it is also, this height, it is also equal to 1 over 1.4. So you can see that the height or the probability of all possible values of x is exactly same, which is 1 over 1.4. So we will study this formula, that why the height is 1 over 1.4. So we will discuss the density function of uniform distributions in the coming slides. So you can see that this uniform distributions, it is just looking like a rectangle. So that's why it is also called a rectangular distribution. So in common with all the continuous random variables, the area under the function between all possible values of x, where x is a uniform random variable, so total area is equal to 1. So this total area is of this rectangle, it is equal to 1. So, and as a result, it is possible to work out the probability density function of x for all uniform distributions using a simple formula. So we can define the probability density functions using one simple mathematical formula. So let us formally define the uniform distribution. So given that a continuous random variable x has possible values from a to b, so x lies, a is less than or equal to x, and x is less than or equal to b, so it means this random variable x, it is taking all possible values from a to b, where a and b are any constants, so such that all possible values are equally likely. So all values which are occurring within this interval from a to b, they have the same chance of being occurrence, so that means they are equally likely. So it is said to be uniformly distributed if all values are they have equal chance of occurrence. So mathematically we write it as that x is a random variable which is distributed as uniform between a and b. So a and b are called the limits of this uniform distribution. A is the lower limit, b is the upper limit. So the probability density functions PDF of this random variable x, which follows uniform distribution, is given by, so f of x is equal to 1 over b minus a, and this is for x lying between a and b. So when x lies between this range a and b, so then these functions, the density functions, are probability density functions, which is also called PDF. It is equal to 1 over b minus a, and the density function is equal to 0 otherwise or elsewhere. Elsewhere mean when x is greater than b or when x is less than a. So it means whenever x takes values other than this interval, so then this function will be equal to 0. So this is the density function or probability density function of a uniform random variable x. So we can draw the graph of this density function. So by drawing a rectangle, so note that here is point A on x-axis, the second is point B. So A can be suppose 1 and B can be suppose 5, or A can be any other number. So B is some number which is greater than number A. So A and B are any constants. So you can see that whenever this x lies from this interval to this interval, from A to B, both inclusive, so then this functions f of x, it is equal to 1 over b minus a. So this height is equal to 1 over b minus a. So this height is 1 over b minus a. So you can see that this uniform distributions, it forms a rectangle. So from A to B with height proportional to, with height equal to 1 over b minus a, whereas this length of rectangle is from A to B, or this distance. So this distance is actually b minus a. So and this height is this is the height, or this is the length of rectangle. So if we calculate the area of rectangle, so area is length into width, or length into height in this case. So actually length is b minus a and width or height is 1 over b minus a. So b minus a cancels with b minus a, so total area of this uniform distribution is equal to 1. And note that whenever this x takes value greater than b, or x lies left to the left of a, or x takes values less than a, so this area represents all values of x where x is greater than b, and this area represents values of x where that are less than a. So you can see that the probability is 0 for all values greater than b and less than a. So while when x lies between a and b, where a and b both are inclusive in this range, then the height or width is 1 over b minus a, which is this probability. So this is how the probability density function of a uniform random variable x is defined. So note that the uniform distribution has two parameters, a and b. So these a and b, they are the two parameters of the uniform distribution. So now let us discuss some of the properties of uniform distribution. So let x be a random variable which follows uniform distribution, ranges from a to b. So then the mean of x, this random variable x, it is a plus b over 2. So mathematically we write it as mean of this random variable x, or expected value which is mean, it is a plus b over 2. So now I am going to prove it. I am going to prove this result, that mean is equal to a plus b over 2. So note that the uniform distribution, its density function is defined as, it is equal to 1 over b minus a when x ranges from a to b and it is 0 otherwise. So now using this density function we can calculate the expected value of x. So since x is a random variable, so the formula for expected value of x, it is integral from minus infinity to plus infinity x times f of x dx. So here in this case we can write this as minus infinity to since as far as this random variable x is concerned, we can see that from a to b the density function is equal to 1 over b minus a, whereas elsewhere it is 0. So we can subdivide this range from minus infinity to plus infinity into different categories, so different intervals from minus infinity to a x f of x dx, and then integral a to b x f of x dx, and then plus integral from b to plus infinity x f of x dx. So you can see that I have subdivided this full range from minus infinity to plus infinity into three integrals. First integral taking values from minus infinity to a, then second from a to b, then from b to plus infinity. So now in next step write this first integral as it is, and then this x, and then the value of this function f of x. So since the range of x for this first integral is from minus infinity to a, so it means it is occurring in this area otherwise, because this range is not covered in this first option where x takes values from a to b. So it means this function when x ranges from minus infinity to a, it is 0. So x times 0 dx plus a to b, and then this x as it is, and then this f of x when x lies between a and b both inclusive, so it is f of x equals to 1 over b minus a. So 1 over b minus a dx plus b to plus infinity this x, and similarly this f of x is 0 for this interval. So we can simplify it. So x times 0, it is 0, so integral of 0 is 0, and then we will write this second integral as it is. So x into 1 over b minus a dx, where range of integral is from a to b, and this is also 0. So it means the simplified integral is from a to b. Since 1 over b minus a, it is a constant, so it can be taken outside the integral. So we are left with only integral of from a to b x dx. So it means now we have to integrate this x. So write this b minus a as it is. So from basic algebra we know that integral of xn dx, it is xn plus 1 over n plus 1. So here x raised to power 1. So it means from this formula, if n is 1, so integral of x1 is, according to this formula, it is 1 plus 1 over 1 plus 1, which is x square over 2. So writing this integral as x square over 2, and then a to b, which are the limits of integration. So now expected value of x, it is 1 over 2 times b minus a as it is. So I have taken this 2 is constant number, so you can multiply with b minus a, and now just apply limits of integral to this x square. So replace x by upper limit, so it will be b square, and then put a minus sign and then replace this x by the lower limit. So it is actually b square minus a square. So in next step, write this denominator as it is, and from basic algebra we know that b square minus a square, it is b minus a and b plus a. So from here you can see that b minus a cancels with b minus a, so we are left with b plus a over 2, which is the expected value of x, or we can write the expression in arranged form. So a plus b over 2. So this is the expected value or mean of random variable x, which follows the uniform distribution. So mean of random variable x is a plus b over 2. So next property is that variance of random variable x, which follows uniform distributions from a to b, then variance is b minus a whole square divided by 12. So now in order to prove it, we know that the variance of random variable x, it is defined as expected value of x square minus expected value of x whole square. So we have this expected value of x, which is the mean of random variable x, which is a plus b over 2. We have just calculated it. So it means in order to calculate variance of x, we need expected value of x square. So let us calculate expected value of x square first. So expected value of x square is minus infinity to plus infinity x square times f of x dx. So note that I am using the integral sign because x is a random variable which is a continuous random variable. But when x follows x is a discrete random variable, then there is no need to use integral sign. Then in that case you have to use the summation sign. So currently this e x square, expected value of x square, is integral from minus infinity to plus infinity x square into f of x dx. So we can see that we can subdivide this integral, the range of x from minus infinity to a, which will be 0, and then from a to b, and then from b to infinity, plus infinity. So that will also be 0. So I am considering only the integral which ranges from a to b. So and then this f of x is 1 over b minus a, so dx. So taking this constant 1 over b minus a outside the integral, so we are left with x square dx from a to b. So this 1 over b minus a as it is. So now the integral of x square is x2 plus 1 divided by 2 plus 1. So it is x cube over 3. And then the limits of integration a to b. So we can write it as 3 times b minus a, and then here we have to apply the limits of integration. So it is x cube, so replace x by the upper limit, so which will be b cube minus a cube. So write the denominator as it is. So this b cube minus a cube, we can write it as b minus a into b square plus ab plus a square. So this is basic formula of algebra. So b minus a cancels with b minus a, so expected value of x square, it simplifies to b square plus ab plus a square whole over 3. So now we have calculated expected value of x square, and we have expected value of x already calculated, which is a plus b by 2. So we can use this formula of variance, Vx is equal to ex square minus ex whole square, to calculate variance of x. So now use this formula. So variance of x, it is expected value of x square, so which is calculated to be b square plus ab plus a square divided by 3 minus expected value of x whole square. So expected value of x is a plus b over 2 and whole square. So put square on this whole fraction. So now simplify it. So write the first fraction as it is, and then here it is a square plus 2ab plus b square divided by square of 2, which is 4. So now take LCM of 3 and 4, which is 12. So 3 4 the 12, so multiply 4, so it is 4b square 4ab 4a square minus, so 4 3 the 12, multiply 3 with each of these three terms, and remember that here we have negative sign, so you have to be careful. So I am writing this expression within the parenthesis. So multiply these three terms with 3, so it is 3a square 3 to the 6ab plus 3b square. So now simplifying it, so it is 4b square minus 3b square, so we get 1b square, and here we have 4ab and it is plus into this minus 6ab, so we get minus 2ab, and here we have plus 4a square and this is minus 3a square, so we get plus a square whole over 12. So you can see that it is b minus a whole square divided by 12. So this is the formula for the variance of x. So variance of x is b minus a whole square over 12. So this is how we can use the simple formula of integration to calculate the mean and variance of a random variable x, which follows uniform distribution. So next we discuss the concept of standard uniform distribution. So note that if x is a random variable, continuous random variable, which follows uniform distributions from a to b, so then the density function is 1 over b minus a when for x ranges from a to b, and it is 0 otherwise. So but when this a is 0 and b is 1, that is x is a uniform random variable from between 0 and 1. So then this uniform distribution has a special name, and it is called standard uniform distribution, and we can write its probability density function by just replacing b by 1 and a by 0 in this original probability density function formula. So we can write it as f of x is equal to 1 over 1 minus 0. So 1 over 1 minus 0, it means it is 1 when x lies between 0 and 1, where 0 and 1 both are included in this range. And this f of x, it is 0 otherwise. It means when x is greater than 1 or when x is less than 0, the value of this probability density function, it is 0. So this is called standard uniform distributions. So in case of standard uniform distribution, the range of random variable x is from 0 to 1. So now let us discuss the cumulative distribution function of a uniform random variable. So the cumulative distribution function of a uniform random variable x is, it is usually denoted by capital F of x, and it is equal to x minus a whole divided by b minus a, where a and b are any two constants such that a is less than b. So here I have drawn a figure showing the cumulative distribution function of random variable x. So you can see that whenever x lies to the left of A, so in this area, so then the distribution function, it takes value 0. So but when x lies from A to B, so you can see that this distribution function is showing us an increasing pattern and it goes up to 1. So here at B it goes up to 1, and whenever x takes values beyond B, greater than B, so this f of x, it still takes value 1, so it keeps the same level 1. So we know that the cumulative distribution function, it ranges from 0 and 1, it cannot be bigger than 1. So since for uniform distribution, the density function, it takes a positive value when x lies between A and B, and it is 0 otherwise, whether x is less than A or x is greater than B. So so that's why in order to calculate the CDF or cumulative distribution functions, all values of x which are less than this lower limit, they are 0. So but all values which are greater than B, since we are adding all values together, so their sum is already 1 till B. So that's why all values which are greater than B, their sum will be still 1, because all values which are greater than B, their probabilities are 0. So it means 1 plus 0, there is nothing is being added. So it means the probability will remain same to 1. But when values of random variable x, they are less than A, so the probability of all values which are less than A, that is 0. So that's why we are showing we are seeing this CDF which takes value 0 when x is less than the lower limit of uniform distribution. So here from figure f of x is 0 when x is less than the lower end point of the support A in this case, and this f of x, the CDF of x is 1 when x is greater than the upper end point of the support, which is the point B in this case. And the slope of the line between A and B, it is 1 over B minus A. So using these three ideas, we can write the complete CDF of random variable x which follows uniform distribution, that whenever x lies to the left of A, this area, so this CDF is equal to 0, and whenever x takes values between A and B, it means this full area. So this CDF of is 1 over B minus A times x minus A, and whenever x is greater than B, it means this full area x greater than B, so this will be equal to 1. So now let us discuss some of the applications of the uniform distribution. Perhaps not surprisingly, the uniform distribution is not particularly useful in describing much of the randomness we see in our real life. So its claim to fame is instead its usefulness in random number generation. That is, approximate values of the uniform distribution between 0 and 1. This can be simulated on most computers using a random number generated. So the generated numbers can then be used to randomly assign people to treatment groups or in the control groups in different experimental studies. Or we can also use the random numbers which are generated from the uniform distributions to randomly select individuals for participation in a particular survey. So now let us discuss some of the applications of uniform distribution. So perhaps not surprisingly, the uniform distribution is not particularly useful in describing much of the randomness which we see in the natural world around us. So its claim to fame is instead its usefulness in random number generation. That is, approximate values of uniform distributions between 0 and 1 can be simulated on most computers using a random number generator. So the generated numbers can then be used to randomly assign people to treatments in experimental studies, or we can also use these random numbers which are generated from uniform distributions between 0 1 to assign peoples in the control group. Or we can also use uniform random numbers which are generated from uniform distributions between 0 and 1 to randomly select individuals for participation in a particular survey. So before we explore the above mentioned applications of the uniform distributions, it should be noted that the random numbers generated from a computer, they are not technically truly random. Why? Because they are generated from some starting values which are called the seed. So if the same seed is used again and again, the same sequence of random numbers will be generated. It is for this reason that such random number generation is sometimes referred to as pseudo-random number generation. So this word pseudo is added. So yet, despite a sequence of random numbers being predetermined by a seed number, the numbers do behave as if they are truly randomly generated, and are therefore they are very useful in the above mentioned applications. So they would probably not be particularly useful in the application of internet security, however. So let us discuss how we can use random number, how we can generate random numbers in MS Excel spreadsheet program. So there is a built-in function in MS Excel which is called the rand function, which is used to generate uniform random numbers between A and B. So it is equals to rand and then the small parenthesis, there are two parentheses, open and closed. But if we want to generate uniform random numbers within certain limits, instead of between 0 and 1, suppose we want to generate uniform random numbers between A and B, where A and B can be any two numbers, they can be 0 1, they can be other than 0 and 1. So then we can use the same rand functions with slight modifications to get a uniform random numbers within certain limits A and B. So in order to generate uniform numbers between A and B, the formula is equals A plus rand times B minus A, where A is the lower limit and B is the upper limit of the sequence. So for example, to generate uniform random numbers between 10 and 20, so in that case we will replace this A by 10 and B by 20. So just replace A by 10 here. So this formula will be 10 plus rand times B minus A, 20 minus 10. Or you can simplify it. So 10 plus rand times 20 minus 10 is 10. So by using this formula we can generate uniform random numbers within between any two given limits. So let us do the Excel demo. So suppose I want to generate a uniform random numbers between 0 and 1. So just type equal and then the rand function. So equal rand and then the two parentheses, open parenthesis and then close it. So just press enter. So you can see that the randomly generated number is 0.2947. Since this is a random number, this is a random numbers, so by using this rand command, whenever we make any change in Excel spreadsheet, that command will be rerun and we will get a new number in place of this number. So you can press the del button from your keyboard. So just take this keyboard cursor to any blank cell. Currently this keyboard cursor is in D5, and then press del from your keyboard. So you can see that this time the randomly generated number is 0.92557. Now press del again, it is now this time 0.21362. So keep pressing the del from your keyboard. You can see that each time we are getting some different random numbers, and note that all these random numbers, they are between 0 and 1. So this is how we can use the rand function to generate uniform random numbers in Microsoft Excel spreadsheet program. Now suppose you want to generate 10 uniform random numbers, or you want to generate hundreds of uniform random numbers. So just type this command one time in MS Excel and then take your mouse cursor to bottom right corner and select it to your desired limit. So suppose we want to generate 10 random numbers, so drag it up to row number B11. So that's it. So here is the list of 10 uniform random numbers between A and B. So just press del from your keyboard. You can see that all are being changed. Why? Because rand function is used, which actually recalculates the random number, or the command is rerun every time when we make a change in our Excel spreadsheet. So you can either press del from your keyboard, or you can write anything in MS Excel spreadsheet program. So whenever we make a change in Excel spreadsheet program, the command will be rerun, we will get a new random number. So just press enter. So you can see that we have a new set of 10 uniform random numbers. So now delete this entry. So you can see that we are getting a new set of uniform random numbers between 0 and 1. So now suppose we want to generate uniform random numbers between A and B. So to generate uniform random numbers, between A and B, the command is A plus rand times B minus A. So now suppose we want to generate uniform numbers between 10 and 20. So we want to generate a uniform random number between 10 and 20. So the command is just replace A by 10. So 10 plus rand times B minus A. B is 20, 20 minus A, so 20 minus 10. So this will give us a uniform random number between 10 and 20. So just press enter. You can see that the randomly generated uniform random number is 14.9014. So again press del from your keyboard. So you can see that this time it is 10.58. Again press del from your keyboard. 10.60, 18, 16, 19, 13, 16, 14, 17. So you can see that we are getting different uniform random numbers, and they are all lying between 10 and 20. Now suppose you want to generate, let's say, 5 uniform random numbers between 10 and 20. So you can select, drag this range up to your required limit. So here is the list of 5 uniformly generated random numbers between 10 and 20. So now suppose, as a real world example, suppose we want to select 20 individuals. Suppose, so now let us discuss one important use of uniform random numbers. So suppose we have a class of, let's say, 20 students, and we want to select 3 students out of 20 students in such a way that the chances of all the 20 students, they are equal. So each of the 20 students has an equal chance of being selected, and we want to select, suppose, 3 students. So in order to select 3 students, so we can use 0 plus, so we can generate random numbers actually from 0 to 20. So rand times 20 minus 0. So this command will generate a uniform random numbers from 0 to 20. So press enter. So it is 14.15. So just round this number. So it is 14. So it means the first selected student will be the student having roll number or serial number 14. So just drag it down. So here just round all 3 numbers. So first is 3. So it means first selected student is the third student, and this is rounded to 1. So it means next selected student is student having roll number 1, and next one is roll number 4. So if you press del from your keyboard, so next time the selected students, they are student 1, 7th and 5th. So now this time the student 13th, 11th and the 8th student. So this is how we can use uniform random numbers to select certain individuals while conducting different types of surveys. And remember that this will be called simple random selection. So we have given each of the 20 individuals or students an equal chance of being selected. So here, by using this rand between function, a rand command, so we can select uniform numbers. We can select 3 students in such a way that chances of a selection of all 20 students, they are equal. So we can also generate uniform random numbers using the Excel add-in, which is analysis tool pack or data analysis Excel add-in. So first step to use the analysis tool pack, which is an Excel add-in, is to activate the analysis tool pack. And remember that if analysis tool pack is not already active, so first you have to activate it. So first step is activate data analysis tool pack, and next step is open data analysis tool pack from the data tab, and then select random number generation, and then select appropriate options from the dialog box, whether you want to generate a uniform random numbers or you want to generate random numbers from binomial distributions, or you want to generate a random numbers from Poisson distributions, or you want to generate a random number from normal distributions. So let us demonstrate the same idea in our MS Excel spreadsheet program. So here is our Excel spreadsheet program. So I'm going to open a new sheet. So first go to data tab. So on right hand side, if you do not see the data analysis button, it means this analysis tool pack or data analysis Excel add-in, it is not already active. So you have to first activate this data analysis tool pack. In one of our earlier lectures, I have explained how we can activate data analysis tool pack. So let us repeat all those steps once again in a short way. So go to click on this Excel button, select Excel options, and here on the left hand side select add-ins, and now click on go button, and here is first option, analysis tool pack. Note that the second option is analysis tool pack VBA, Visual Basic for applications. So we need not to select this second option, so just select the analysis tool pack first option and click on OK. So now here is a dialog box that it is asking us that Microsoft Office Excel can't run this add-in. This feature is not currently installed. Would you like to install it now? So click on yes. It may ask you to provide the installation disk, Microsoft Office installation disk. So currently it will take around 1 or 2 minutes to install it or to activate the same add-in. So here is the progress bar. So it is configuring Microsoft Office Enterprise 2007. So it will take some time. So Excel, Microsoft Office has installed it. It will take around 5 to 10 seconds, I think. Okay, here it is. So go to data tab. So here on right hand side we can see the data analysis tool pack. So click on this data analysis tool pack. Here is a dialog box. The name of the dialog box is data analysis. So you can see a number of options here. So here is the option which is random number generations. So we want to generate random numbers. So select this option and click on OK. So here is the dialog box, random number generation. So now just read all the options one by one. So number of variables, how many variables you want to generate. Suppose we want to generate only one variable, so just type 1 here, and then number of random numbers, how many numbers you want to generate. Suppose we want to generate a list of 10 random numbers. And next option is the distributions, from which distribution you want to generate random numbers. So uniform, normal, Bernoulli, binomial, Poisson, patterned and discrete. So suppose we want to generate random numbers from uniform distributions. So next, what are the parameters of this distribution? So between 0 and 1. So if you keep this range 0 and 1, so it will generate a uniform random number from standard uniform distribution. So let us keep the same range between 0 and 1, and here is the random seed option. So if you want to get the output, same output again, so you can put any random seed here. So suppose 1, 2, 3. And next are the output options. So first is output range, second is new worksheet ply. If you want to get the output in a new sheet, so just write the new sheet name. Currently in our Excel spreadsheet we have 3 sheets, sheet 1, 2, 3. If you want to generate, if you want to put the output in new sheet, so just write the name of the new sheet. Our new workbook, in that case currently we are working on this book, which is book 2. So if you want to display the output in a new workbook, so you can select this last radio button. So currently I'm going to select output range because I want to display the results in the same sheet. So click on this button and select any blank cell. So I've selected B2. So click OK. So you can see that these are the 10 random numbers. So uniform random numbers from B2 to B11. And note that these are now fixed. they will not change whenever you will make any change in Excel spreadsheet, just like the in contrast with the rand command. So where the numbers, they keep on changing whenever any change in Excel spreadsheet is made. So now go to data analysis, random numbers. Okay, now suppose we want to display the output to in this cell D2. So since the same random seed is used, so same output will be displayed. So click on OK. You can see that the same numbers have been regenerated. Why? Because the random seed which is used in each case is same. So data analysis, OK. So this time I am going to remove this seed. So, and I want to display the output here in suppose F2. So click on OK. So this time we get a new set of uniform random numbers. So data analysis, OK. And suppose we want to generate uniform random numbers from 10 to 20. So 10 and 20, and suppose we want to display the output here in C2. So click OK. So these are the uniform numbers from between 10 to 20. So go to data again, data analysis, random numbers. OK. So you can change the distribution as well. So let us select the discrete distributions. So you can change the distribution. So let us select the Bernoulli distribution. So go to data tab again, data analysis, random number generations, and now this time select binomial distribution. So number of variables 1, number of random numbers 10, and the distribution is binomial, and the parameters of binomial distributions, the p and the number of trials. Suppose p, the probability of success is 50% or 0.5, and suppose the number of trials are 10. So and the output is suppose here in E2. So click on OK. So these are the 10 random numbers generated from binomial distribution with probability of success 50%, and the total number of trials they are 10. So this is how you can use this random generation options from the data analysis toolpack to generate random numbers from any desired distribution. So let us discuss few examples which are related to uniform random variable. So consider the data on 55 smiling times in seconds of an 8-week-old baby. So 10.4 seconds, and then 12.8, 1.3, 5.8, 8.9 seconds, and so on. So these are the 55 data points which represent the smiling times in second of an 8-week-old baby. So the mean of these 55 data points, which is the sample mean, it is calculated to be 11.49, which is the average of these 55 numbers, and the standard deviation is calculated to be 6.23. So we assume that smiling times in seconds follow a uniform distributions between 0 and 23. Why? Because the minimum number in this range is it is around 0.7, and the maximum number in this range is 22.8. So we can see that we can say safely that the smiling times in seconds, they follow a uniform distribution between 0 and 23 seconds, where 0 and 23 both are included in this range. So this means that any smiling time from 0 to and including 23 seconds is, they are equally likely. So each of these 55 points, they have an equal chance of being selected. So let us define a random variable x, which represents the length in seconds of an 8-week-old baby's smile. So what is the smiling time or smiling length? The notation for the uniform distribution is that X is distributed as uniform between A and B, where A is the lowest value of X and B is the highest value of random variable X. So the probability density function is f of X is equal to 1 over B minus A whenever X lies from A to B and it is 0 otherwise. So as far as this current example is concerned, we can write it as that X is a uniform random variable. It is distributed as uniform between 0 and 23, and the density function of this random variable X is 1 over B minus A. So 1 over 23 minus 0, which is 1 over 23 whenever X ranges from 0 to 23. So just replace A by 0 and B by 23. So note that the theoretical mean or the true mean and the standard deviations, they are in case of uniform distributions, the mean is A plus B over 2 and the variance is, it is B minus A whole square over 12. If we take square root of variance, we get the standard deviation or sigma. So as far as this current situation is concerned, just replace A by 0 and B by 23. So 0 plus 23 by 2, we get 11.50 seconds, which is the theoretical mean of these uniform distributions. And similarly, replacing B by 23 and A by 0 in the formula of standard deviation, we get the standard deviation, which is 6.64 seconds. So note that these are the theoretical mean and standard deviations, which are very close to the sample mean and sample standard deviations. So 11.50 is the theoretical mean or actual mean of the uniform distributions, whereas the sample mean, which is the mean of these 55 smiling times, it is 11.49. So similarly, this sample standard deviation, it is very close to the population or true standard deviation. So now let us discuss few problems. What is the probability that a uniformly chosen 8-week-old baby smiles between 2 and 18 seconds? So it means we need to calculate probability that 2 is less than X is less than 18. So as far as this figure is concerned, so this uniform ranges from 0 to 23, and currently we need to select, we need to find the probability from 0 to 18. So this shaded area is our required area in this case. So we can calculate this probability by using the formula for finding the area of rectangle, which is base times height. So in order to find this length of this rectangle, so we have to move from 2 to 18. So which is 18 minus 2, which is 16 unit, and this height is, height of rectangle, it is 1 over B minus A. So 1 over 23 minus 0, which is 1 over 23. So 18 minus 2 times 1 over 23. So 18 minus 2 is 16 over 23. So the probability is 16 over 23 that a randomly chosen 8-week-old baby smiles between 2 and 18 seconds. So let us discuss another problem. Find the 90th percentile of an 8-week-old baby's smiling time. So 90% of the smiling times fall below the 90th percentile. Suppose the number k. So we can say that probability that X is less than the number k, it is 0.90. So what is this particular value? That below this k we get 90% of the probability or 90% of the area. So as far as this diagram is concerned, note that this height, it is 1 over b minus a, which is 1 over 23, and the range of uniform distribution is from 0 to 23. So we need to calculate this number k below which 90% of the area lies. So this shaded area is equal to 0.90 or 90%, but what is the number k? So find the 90th percentile for an 8-year-old baby's smiling time. So we need to calculate this particular number k. So note that probability x less than k is 0.90 or 90%. So we can again calculate this probability. It is the base times height. So we can calculate this base from 0 to k, it is k minus 0, and the height is 1 over b minus a, which is 1 over 23. So k minus 0 times 1 over 23, and on right hand side we have 0.90. So just shift this 24 for the 23 to right hand side. So 23 is being divided, so when it will be shifted to right hand side, it will be multiplied with 0.90. So k in this case is 20.7. So this number k is 20.7. So 90th percentile is 20.7. So this is the point below which we have 90% of the area. So let us discuss another example. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. What is the probability that a person waits fewer than 12.5 minutes? So in order to answer this question, let us define a random variable x, which represents the number of minutes a person must wait for a bus. So since the range is from between 0 and 15, so we can safely say that a is 0 and b is 15. So x is distributed as uniform between 0 and 15. So the probability density function is f of x is 1 over b minus a, which is 1 over 15 minus 0, and this is 1 over 15 when x lies between 0 and 15 both inclusive, and this f of x, it is 0 otherwise. So question is, what is the probability that a person waits fewer than 12.5 minutes? So it means we need to calculate probability that x is less than 12.5 minutes. So first draw a graph. So the range is from 0 to 15 and the height is 1 over 15. So this distance height is 1 over 15. So we need to calculate probability x less than 12.5. So 12.5 is here, somewhat here. So it means we need to calculate this shaded area. So probability x less than 12.5. So 12.5, it is base times height. So base is this area, so which is 12.5 minus 0, or it is actually 12.5, and height is 1 over 15. So 12.5 minus 0 times 1 over 15, so it is 0.8333 or 83.33%. So we can say that the probability a person waits less than 12.5 minutes is 83.33%. So let us review the main concepts which we have discussed in today's lecture. In today's lecture, we have discussed probability distributions of a continuous random variable, and in particular we have discussed the uniform distributions and some of the properties of uniform distributions, and we have also discussed how we can generate uniform random numbers in MS Excel. And we have also discussed some of the related examples which are related to uniform random variable. So in the next lecture, we will discuss the normal distributions, which is also used for the continuous random variable. and we will discuss probability density functions of normal distributions, and we will discuss some of the important properties of normal distributions, and we will try to cover some of the related examples as well. So till then, Allah Hafiz.